get started with the next session. We're running a little bit behind. We don't want to keep you guys here too long. We've been here since pretty early. So we're not going to go over all of the solutions to the breakout session that Paul just gave. We will post those online. If you have any questions, we'll be sticking around afterwards. Feel free to grab us, bother us about some of these things. My name's Brad, by the way. I don't think I've met most of you. I'm going to talk about, for the first time, we're going to do some actual, real, substantive, at least the infrastructure you need to do real substantive mathematical calculations. I think a lot of people here are coming from the physical sciences, social sciences, people who are dealing with reasonably large data sets. So the idea behind this session is to give you an introduction to some of the Python packages that you will need to handle large amounts of data. The two packages are called Numpy, and then to actually plot that data called Matplotlib. If you're on the agenda website, there are a couple different ways you can follow along. I know some people had questions about how to get the notebook started, all that stuff. Right there is a link to the PDF of the lecture slides that I'm going to give. So you can download that and follow along. I also made a notebook with most of the code that's going to be on my slides. You can grab the PDF version. You can grab the raw version and enter it in the notebook itself. I'll show you how to do that in a second. If you just click on the HTML viewer, it renders it in HTML. So you can't actually click on any of these cells. It won't do anything, but you can see what's going on. And if you download the raw notebook and save it within the extension IPNYB, we can fire that up. Just again, start up the notebook, iNotebook, IPython notebook. I'm going to add 2 flags here because I'll be stepping through some of this. The PyLab loads a bunch of Numpy and Matplotlib packages that are useful, and inline argument tells it to put the plots inline. I'll show you what that means in just a second. But how to load this up, right? We fire up the notebook. It says it's launching. It shows us here something in our browser. We have a single IPython notebook that's in that directory. It already knows where to look. We fire that up. Just click on it. And in a second, it'll have the full notebook here. So you can step through, and almost all, there are a couple changes I made at the last minute, but almost all the code that I'm going to be showing in the slides is in this notebook. So instead of you guys having to type it, you can step through and see what it looks like there. Yes, questions? Sorry, go ahead.
Can you show the code again?
To start up the notebook, it's this line right here. So you call IPython, and then you add the notebook argument to it. That should start up a new window in a web browser if you have a web browser open.
And what additional functionalities are you adding by doing the PyLab and the inline?
I will show you as we get towards the end of the lecture. If I don't, remind me at the end. Yes?
Can we open up the specific .py?
Right, so I'll do this one more time to show you what happens. Let's kill these. Okay, so I have a single .ipynb file in this directory. It's called numpy plus matplotlib. I just grabbed it off the website. I type IPython notebook, a couple extra flags here, get it up and running, enter. It automatically takes me, once it gets the kernel up and running, over to my web browser. It starts the notebook and lists all of these .ipnyb files that it finds in the directory that you started IPython in. In this case, there's only one. I go over there. You can see I have a hand now when I select it. I click on it, and it loads that notebook up. Okay? Okay. So here we are. Again, Numpy, which provides you with a capability that we're going to call an array, and Matplotlib plotting. The reason why most of you, we think most of you are scientists. We hope that if you ever get an Excel spreadsheet from someone, maybe think, ooh, I don't know if this person really knows what they're doing. But if you send them a notebook or a Python file or something like that, You'll seem very impressive even if your work is not. That's how I've gotten by so far. Array creation and basic operations. I'm going to introduce you to this idea of what a universal function is in broadcasting. It's a very powerful tool in Python, but it operates somewhat different from the rest of the things that we've seen so far today. Some basic comparison testing, selection, and manipulation of arrays. The NumPy module provides some basic statistics capabilities. You'll get a lot more in SciPy, which we'll talk about, I believe, tomorrow on Wednesday. And then how to make some basic plots. You want to put nice, pretty things in your paper. The array class. We're going to talk about object-oriented programming. But essentially what NumPy provides is access to this thing called an ND array. Okay? And the ND array is exactly what you think it is. It's an object. Okay? It represents a multi-dimensional. In the same way that a list is, it can have any number of dimensions. Sorry, not in the same way that a list is. It can have any number of dimensions. But what's very important is that all of the items in this array are homogeneous. Okay, they're a fixed size and a fixed type, and changing that makes a big difference, right? So you can imagine, let's say I have a list. We saw it before. You can have a list. The list can be composed of integers, strings, other lists, whatever you want. Python doesn't care. It doesn't really matter. Okay? But when you're specifying an array at the outset, you're going to tell it what the individual items, the constituents of this array, what they look like. They need to be fixed size, fixed type, because some of the operations we're going to perform on the array take advantage of that fact. I'll come back to that in a second. I think it's pretty easy just to learn from looking at a few examples. How do I create one of these NumPy arrays, these ND arrays? You're never going to really call the ND array method itself. Usually it comes from other methods that will return you an array. So to get started, we import the NumPy package. It's traditional to call that as NP, just to save us a few letters when we're typing. One of the questions we heard earlier is, what is the PyLab flag? When I started IPython earlier, it does this to start off with. This is one of the things that loads into your namespace. And we can start with our very simple first array. A equals np.array has 3 items, 1, 2, and 3. Go here a little bit. So I can print that, show you what kind of representation it has. Not surprising, very basic array. The ones method or function will give you an array where every item is a 1. If you pass an argument to it, a single tuple, that will change the size of the array that it returns. So this will return you set to be an array that has 3 rows or 2 columns or 3 items in the first dimension and 2 in the second dimension. Okay, if you want to think about multi-dimensional items. Each array, ND array, has a property called its shape. This is a tuple that tells you, describes how the geometry of the array. Zeros, like ones, returns an array that instead is populated by zeros. If you pass 2 arguments to something that generates an array like this, the second one will specify the type of the things that are in your array. So in this case, it's a 1 by 3 array with all integer 0 values. If I look at the type of C, it's an ND array, which is what I said it was before. But if I look at the D type, okay, this is a property of the ND array, again, in the same way that shape is. That specifies that all of the individual items are 64-bit integers. Okay? Lin space, someone was asking before, is there a way to create arrays with not, this one, in this case, it's actually fixed the spacing. But this will generate an array. It will go from 1 up to 5, again, not inclusive on the 5, and there will be 11 points in between there. There's a corresponding, if you want logarithmically spaced arrays, np.log space will do that. Oh, sorry, 1 to 5 inclusive in this case, and 11 points in between there is what the linspace method does. So I was saying about types before, why it's important that all of these things have the same fixed type. So if I create an array and I give it 3 items, I give it 1, 2, and 3.0, it's going to create an array and it's going to use the sort of smallest representation that it can that will accommodate all of the things that you feed it in there. So here you have an int, and a float. The float is larger than the ints, so it will use the float when you initially create the array, and it will cast everything in this array to a float. So all of the items are going to be of type float in this case. If I send it integer 1, integer 2, and string 3, the smallest thing that will accommodate those is actually a bit surprising. It's a 1-character string. Okay? So it casts everything now as a 1-character string, S1. That's what the D type is telling you about. If I try instead to set the last item of this array to something that's not a 1-character string, strange things are going to happen that you're probably not going to like. In this case, it's going to just cut off everything there and use the first character of this as a string. Okay, so unlike everything else in Python, where there's a lot of freedom and flexibility in defining the types of variables that are stored in your variables, it's very important that you pay careful attention to what types of things you're setting in this. Here's one more example. If I have 3 integers, if I try to set the first one to 1.5, it's going to just treat that as a single integer 1. If I try to change the D type of this array to a float now, that's really going to throw it off because it's set aside certain parts in memory. If I then try and read C, it's going to give me something nonsensical back. Okay, because it's actually reading into memory that it sort of didn't allocate initially when the sizes of these things was quite small. Okay, so be careful about, so yeah, I guess this is another meme for Josh here. Honey Badger doesn't use NumPy arrays because NumPy arrays actually care about the type of things that you're putting in there, and he doesn't care about that. Okay. Yes, of course. Go ahead, ask your question. I'll bring it up here in just a second.
C equals the array 1, 2, 3, and then C equals 0 is 1.5, I think.
Yep.
What's going on there?
This array is storing these 3 things as integers. Okay? So I'm saying I want the first item in this array to be an integer. It's just hacking off everything that comes after the integer part of that number and setting it to 1.
So you're saying C of 0 is 1.5, and it says no, it's not.
I'm saying I want C of 0 to be 1.5, and it's saying all the things in this are integers. I can't store 1.5 there. Okay, you can also read arrays from files. This is something that you'll be doing hopefully from your homework. I have a small file. You don't need to download it, but you can just read it. It has 2 lines with the numbers 1, 2, 3, 4, data.text there. The load text method will just read this into an array, and you can see here it's in a 2x2 array where it reads them, in this case, as floats. It also allows you to write out to files. If you just said to file, your array, it will write it out in binary format. You can also tell you if you want it to write out, in this case, as floats with a comma separation between all the individual items. So then if I go back and look at, I call this data.out1, it tells me it's a binary file. It's not really much interesting to see. But if I look at the second one, there are actually the numbers from my array. I changed them. It should be a 1 with comma-separated variables. There are lots of things that will allow you to read comma-separated variables, FITS files if you're an astronomer, even pixel values from JPEG. These are all provided in various NumPy and also Matplotlib modules for you to read in data. Arrays do work like lists in that you can index and slice over them in the same way that you can do with lists. So you can imagine the A range creates an array with items in the same way that range and X range do for lists. So now I have a 10 item array running from 0 to 9. If I want to grab the second one there, that's number 2. if I want to grab from 2 to 5, if you remember how sort of strings were indexed, or lists were indexed in that way from 0 out to n, that will return me a subarray of some of these items. In addition to 2 things, I can say I want to take A from the beginning to item number 6 in steps of 2 and set that equal to minus 1,000. So that will change A so that A sub 0, A sub 2, A sub 4 have all now been replaced. Okay, so the syntax for this is starting point, ending point, and increment between those. Your increments can be negative. So if you want to reverse an array simply, you can just say from start to end where my increment is minus 1. It'll spit it back out in reverse order. And you can also wrap around arrays nicely. That's not necessarily capable in some of these other things. So, no, sorry, not wrap around. If I want to go, say, if I don't know how big my array is to start off with, but I say I want to start from 2 to 2 from the end and only grab the middle ones, that will work to do that. Yes?
Is there a way to separate reading a file, like a CSV?
Mm-hmm.
Is there a way to, so sometimes if you start like importing, even though you define your separation, the first line actually isn't in that same format. Is there like a
Yes, so there's most of the load CSV or load text will have an optional flag called skip lines, or there's also like a comment line. So a lot of lines have pound signs in front of them. Those are options that you can pass to them as well. All right, structured arrays. So everything that I've shown you so far has been pretty simple in that the D type has been an int or a float or something singular like that. But it's actually, you can put together very complex data types into each of your individual items in an array. It need not be that straightforward. These are generally called structured arrays, and you can specify that with the D type. So in this case, I want to create an array that has this size where my data type, where each individual element is going to be 0, but all of the zeros are going to be represented slightly differently. So I'm going to have a 4-bit integer, a 4-bit floating point number, and a 10-character string. Okay? So what does that look like? What does 0 look like in those different formats? 0 integer, 0 floating point, 0 as a 10-character string is actually just an empty string for this representation. And it also returns this D type, which tells me that the first item, the first object in each array item is named F0, and this is its type, I4, again, a 4-bit integer. The second one is F1 with this type, and the third one is F2. So for a structured array, there's a very nice way that you can access all the individual columns, if you will. If I just say X sub F1, it's going to give me all of the things that fall in F1. In this case, all of the floating point representations of 0, and it returns them with the floating point data type. And I don't think we've talked about copying and referencing too much, but something you want to be very careful about. If we assign y to be x sub f1, these zeros here, we're actually pointing y to that memory space. So if we then change y, in this case we add to it another array with 1, that will change x as well. Okay, this is something subtle. I think we'll talk about it more tomorrow, copying, referencing, and how deep your assignments are. But this is something you want to be careful about. Yes?
What does the F stand for?
It's just a default, like F. I'm not sure what the F, like YF as opposed to J, K, or whatever. But it's just telling you this is row 0, this is or column 0, this is column 1. And you will use this in your homework for today. So this will make your homework today much easier to use this. Universal function. The reason why the definitions of NumPy arrays are so strict is precisely for this. There are a number of very basic functions. Most of them are simple things, mathematical operations, but they can be, in fact, much more complex that will operate on an array on an element-by-element basis. Okay? And the reason why the arrays are defined the way they are is because this can be done very quickly if on sort of under the hood, if NumPy knows how big these things are. So a universal function, really all you need to know without delving in too much of the details, is that these operate on an element-by-element basis on arrays. Okay? So let's get some examples. Suppose I have two arrays. Both of them are 2 by 2. A is 1, 2, 3, 4. B is 2, 3, 4, 5. If I add them, okay, adding in this case is known as the universal function because it works on an element by element. So it adds each of the corresponding elements and puts the output in a new array in that element spot. Okay? That makes perfect sense for adding. It doesn't make quite as much sense for multiplication necessarily, but in fact this is how the multiply routine works. Okay, again, it works on an element by element basis. It's taking 1 times 2, setting it to 2, 2 times 3, setting it to 6, etc. It's not matrix multiplication. Okay? Multiply is a universal function, and it's operating element by element. Power, same way. If you want more matrix linear algebra type operations, those are also capable within Python. There's the dot or inner product. There's also a linear algebra package that will provide those. Universal functions run much, much faster than just simply looping over all the individual items in an array. Here's an example of that. Suppose I have an array A, which is just composed of 500 by 500 random numbers between 0 and 1. B is the same thing. And I want to look at two different ways to multiply them together on an element-by-element basis. I can use the universal function, where I just return A times B. Or I can use the for loop way, where I create a new array, set it to empty, has the same shape as A to start. I iterate over all the items in one dimension. I iterate over all the items in the other dimension. And I set the output equal to the product of the two. Okay, that's basically, element by element, what multiplication is doing. But if I use this time it, this is one of these magic functions within IPython. If you just type this in at the Python interpreter, it won't work. But if you do this within IPython, it will. The first thing takes about 2 milliseconds, on average. Whereas the second one is over a factor of 100 slower. Okay, so if you're actually working with large data sets, if you have really small things, it doesn't matter. You can have for loops, but if you're working with reasonable sized data sets, you should never be iterating over a for loop to get at all the items in the array. It's very bad practice. It leads for very slow code. It's sort of frowned upon. There's another idea, just to introduce this to you briefly. It's called broadcasting. I told you that it was very important that arrays be defined in a specific manner. That's true, but there is a bit of flexibility when you're dealing with universal functions. Suppose I have some array that has 1, 2, 3, because 3 is a floating point number. All these are going to be cast to floats, and I add 2 to that. Okay, if you tried to do that in C, if you tried to do that in IDL, it wouldn't work very well because these are different sizes. But the universal function broadcasts this integer if it can do that in a sensible way to give you some result. And you can imagine, just naively, if I said I wanted to add 2 to this, I probably want to add 2 on an element-by-element basis. And that's what it'll do. And this is the idea behind broadcasting. Okay, you can add arrays of different sizes as long as their sizes are reasonably compatible. If they're not, okay, if I want to multiply something that is 3 by 1 to something that's 4 by 1, that doesn't necessarily have any obvious way to do that. Okay, and in that case, it will throw an exception. You need to be careful when doing this, however. Sometimes it will do some things that are not exactly obvious. There's a very well-defined set of rules, so it will be repeatable, but they're not all necessarily obvious in the way that it does that. So imagine if I have an array that's instead of a 3 by 1, 1 by 3, and then I multiply them together. That will actually not throw an exception, but we'll instead multiply 1 by this row, 2 by that row, and then 3 by that row. It's just something to be careful with if you're actually dealing with arrays of different sizes. There are some very nice and quick ways to do comparison testing and selection. Throw a couple of new arrays in here, 1, 3, 0, 0, 3, 2. Again, on an element by element basis, I want to know if A is greater than B. It does that as a universal function. It returns true, yes, false, false. A equals B. Same things here. And you can also assign that output to a new array. In this case, it's an array. The D type, again, for all of these is Boolean. There are logical ands. In this case, A is greater than 0 and A is less than 3. It will check, again, on an element by element. It'll say, okay, A is greater than 0. It's less than 3. Yes. First one's going to be true. Greater than 0, yes. Less than 3, no. Greater than 0, no. So the output is true, false, false. Logical ORs as well work in the same way. What I use the most, and I think you guys, if you deal with large arrays, will probably use it the most as well, is what's called the where method. So the where method operates in the following manner. Suppose I have some array here. It has 5 items. And I say where A does not equal 0. The first argument to where needs to be some sort of conditional test. If you only send one argument to it, it will return an array of indices where that conditional is met. Okay, that's not extremely intuitive, but this is how it works. So what it'll do is it'll go through the individual elements within A. It will say A is not equal 0. The 0th one, yes, that's true. So it will return 0 index. The first one, yes, that's true. The first index. The second one, no, it's not. So it won't return anything there. The third one, yes. The fourth one, no. Okay? So because it matches in 3 times, it returns a 3-element array back to you. You can do something, if you want to actually extract the items in that array where that is true, you can do that with this sort of same syntax as you would use with lists. And instead of giving you the indices where that condition is met, it actually gives you the items where that is met. But what's really nice with where is instead of just providing a conditional statement, you can also say, if this is true, I want you to return this first thing. Or if it's false, I want you to return this second thing. Okay? So where needs to have either 1 or 3 arguments to it. So in this case, it'll look at A, and if A is not, the individual elements are not 0, it will take the inverse of them. Otherwise, it will return the element itself, which is 0 by construction here. Okay? And again, just to show you how where does indices if you have a multi-dimensional array. So I want to know which elements are greater than 5. It will return a 2-dimensional array because the 2-dimensional array was input, where in this case we're looking at row number 2, 0, 1, 2, position 0. That's the first one. Row number 2, position 1. Row number 2, position 2. All the items where it's greater than 5. So a way to efficiently extract information and do basic comparison tests from your array. Okay, there is the capability within NumPy to do very basic statistics. An array, as I said before, is an object. If you haven't done object-oriented programming, you'll know sort of what that means after Joey talks about it tomorrow. For these purposes, essentially, you can take the mean of it very simply. For a 2-dimensional array, it's not exactly obvious what the mean means, but it just takes it by all elements. You can tell it to look over a specific axis if you want. 2 different ones will give you, obviously, different responses. You can take the standard deviation of your array, again, on an element by element basis. In this case, we're calculating the average where we're inputting in the array range, the list range there, and we're giving it some weights to work with. There's the random module, which I talked about briefly before. If I random.rand gives me a random 5-element array with random numbers uniformly distributed between 0 and 1. Rand_int gives me a random integer between 5 and 10, greater than or equal to 5, less than 10. And you can also do a few basic well-defined distribution, the normal distribution, the Poisson distribution. So this samples something on the normal distribution where the mean is 1.5 and the sigma is 4.0. If you want more complicated distributions, these are all in the SciPy package. Yes, the question?
Maybe you're going to cover this, but how do you point it to a large data set that you want to read?
How do I point it? Like if I want to read in a file or something like that. So there's the load text, if it's a text file. There's the load CSV, if it's like a comma-separated variable file. I can point you to a number of places where it'll show you how to read in different types of input files that are either coming with the Numpy or the Matplotlib package. But I mean, as we've been saying before, someone has built capabilities to read in almost any kind of file that you want. Okay, Matplotlib. Let's say we want to make some plots. I'm going to jump over to the notebook here because I think it looks a little better in that case. But it's also on my, the same thing is on my slides. The other thing, as I said, that this PyLab flag will do is it will import matplotlib.pylab as PLT. This is the module or the package in which a lot of the basic plotting capabilities are installed. You'll also see this matplotlib.pyplot. There are a few subtle differences between what it's actually importing, but for our purposes, this is sort of identical to what Paul was showing earlier, import as PLT. The basic command you're going to use from this module is called plot. You can imagine I calculate some very simple arrays here. Here I create one that has 1, 2, 3. I use this universal function to square it. I plot x and y, and the third optional argument that I pass is something that tells me about how to actually put the points down there. If you've ever used MATLAB before, okay, this is very MATLAB-like syntax. The RO says I want red circles for my points. And if you remember before when I started IPython, I started it with the inline flag at the end. Basically all that means is that the plots will be showed in this notebook window instead of a new window popping up separately. Okay? So a very simple plot, as I said before, 1, 2, 3, and the square of that on the x and the y axis. We can do some other very basic things. I create an array where I want linearly spaced data between 0 and 2 pi, and I want 300 points between them. And then I want to take the sign of those, again, on an element-by-element basis, and plot that. You can see here, all I'm giving it is x and y. It automatically sets the scale. It automatically does the tick marks. In this case, it automatically chose the blue line for the color. All these things are customizable. I'll show you how to do a few of them. But it does a pretty reasonable job creating the plot to start out with. This is a slightly more complicated example if you want to know how to change, say, the axis labels or the title of the plot. In this case, again, I'm taking the sign, and I have the sign of x, y. I have the sign of x squared is y2. I can plot x and y, and this label will create a label for the legend. And you can see, if any of you have ever written in LaTeX before, if I pass it a raw string with some LaTeX math syntax, it will actually properly read that and format it as such. Same thing here. This allows me to change the title. This changes, not surprisingly, the label on the x-axis, the label on the y-axis, create an evenly spaced grid, and give me a legend. And this is the results of the output of that. Okay? What I've shown you here is sort of the very simplest way to interact with the plot command. It's what we'll call like the non-object oriented way, because we haven't covered object-oriented programming. There's a much more powerful way where Matplotlib is actually returning you like a plot or an axis object that gives you basically a much richer syntax to work with. But since this was just an introduction, I didn't want to confuse anything too much. But if you have more questions about that, just let us know at the end. A couple more really basic capabilities that are in Numpy and Matplotlib combined. You can do some very simple polynomial least squares fitting. Suppose I have two arrays, and I want to first fit so I have x and y, which are simple arrays. There is this polyfit, to which I send it the x, the y, and the order of the fit. And that returns what's called like a polynomial structure. It doesn't actually return the values of the fit. You need to then give it a grid on which to evaluate that. So then I take the one-dimensional polynomial and put it onto P. I can do the same thing with a slightly higher order fit, call that P30. And on here, I'm actually creating the grid on which I want to evaluate these polynomials, and I will plot them. And this changes the stretch on the y-axis, the limits over which this is plotted. So you can see here's my original data shown as these blue points. The green is a third-order polynomial fit to them. The red dashed line is a third-order fit, which does a better line, obviously a better job going through the points, but also introduces some very funny behavior there. Not surprisingly, gives you a warning that you're using a much higher order polynomial than you are probably justified in doing. And I think the last thing that I want to show is there's a nice histogram plotting method and a random number generator. So I can create a normal distribution in the random module with the normal method. I give it a mean, a sigma, and a number of points that I want to generate. I can then very nicely just plot that as a histogram. It stretches over a bit here at this resolution. The histogram you can read pretty nicely. That's what it's showing in these blue bars. And then I can plot the actual distribution from which those histogram was drawn. Just a normal distribution spelled out there. And this is what it gives you, so you can see it's a nice capability. The best way, I think, if you actually want to learn how to make some kind of plot in Matplotlib is to look at the gallery. So there's a link at the bottom of this notebook, or if you just do a Google search for Matplotlib gallery. What this shows is, I don't know, maybe a few hundred examples of people who have made all kinds of other plots using Python, Numpy, Matplotlib, and they also have the source code, the source Python that was used to generate all of these. So say you want to do something that, I don't know, as some subplots or something like that, you can click on here, and down here is the source code that was used to generate all that, introduces you to the subplot feature, and shows you how to reproduce a plot like this. And there's a pretty good cross-section of a variety of things.
Right.
Yes?
You just click on the source code, copy that URL, and then in the notebook type in loadpy.
Where did my notebook go? Let me start up another one.
Back button.
Oh, that's right. I left it when I
Sorry.
created that thing. Sorry. Okay, let's create a new one. New notebook. Okay, load pi.
Space, and then URL.
There you go. Unlike, pardon? There you go. There are your plots brought right in. Should be clear, in case it isn't before, that the number of commits that I've made to the IPython notebook is somewhat smaller than the number that Paul has. But that's all right. It shows you that you don't actually need to understand all the guts of these things, I think, to do some nice stuff. All right. So that is everything I think that I wanted to cover. Does anyone have any more questions at this point before we get into the breakout stuff? All right, the breakout problem, which I shamelessly stole from Fernando. For this, let me close some of these, find out where it is. There we go. All right, so there's also on the agenda webpage is the breakout problem in PDF and also in all the notebook formats. The basic idea is that we want you first to reproduce within Python the trapezoid rule. If you're unfamiliar with the trapezoid rule, this is a way to do numerical integration. I'll give you a little bit of background here, where you're just essentially linearly interpolating, taking the difference between 2 points on this curve and summing up the area as you sort of step along to get the integral, an approximation for the integral of a given function. So the first thing that we ask you to do is write a function called the trapezoid that applies the trapezoid formula. If I give it 2 arrays to actually do this sort of trapezoid calculation. Next, once you've mastered that, write a function, write a routine that will take a function f, endpoints a and b, and the number of sample points to take. Sample that function uniformly at these points and return the value of the integral. Okay, so now you're actually taking some function, calculating it at certain points on a grid, seeing the, take a simple function that you can easily integrate, seeing how the trapezoid rules compares to that, depending on how many points you're doing. Show that these are correct by working on a few very simple functions. And if you get all the way down to the end, that would be great. See how that changes as you actually change how fine your sampling is on that point. Just so you know, this shouldn't be too complicated. I mean, the trapezoid rule can be done with just 1 or 2 lines of Python code if you're doing the indexing of your arrays in a smart way. Again, this shouldn't be done with like for loops and stuff like that. It can be done much faster than that. So we'll give you like 10 or 15 minutes, I guess, to work on that.
I think what we'll do, because we're running a little bit late, is also give you the homework problem and then have people who want to stay start working on the breakout, maybe do the breakout solution at the end, and then we'll go over the homework in the morning. Okay. So if you can reload that. Just reload that page. And then click on PDF. Okay, so we want to get you comfortable working with Numpy arrays and get you comfortable doing some plots. We'll ask you basically to use this comma-separated file called trends.csv, which is posted on the agenda site. Using Matplotlib, there's a way to read that in, something called CSV to rec. And you can also use something called load text if you like. There's a bunch of different ways to read in CSV files nicely. And then try to make a plot that essentially reproduces this. What is this? This is a search on Google Trends for a bunch of different words as people are searching on Google. And you can see that there's some seasonality associated with this. Spring break, which is in blue, tends to come right around spring break and right before it. You can see when people start thinking about it. Textbooks, which I've spelled wrong up there, you can see that you wind up getting a lot of searches on that twice a year. You can imagine when that happens. Skiing, you can see which year has probably had a couple of different snowstorms around the country by looking at the double peaks, and kayaking or something. Try to reproduce this plot as faithfully as possible using what we've given you there. Go to the next one. And we're going to actually try to do some numerics on this, try to get some insight out of that data, determine in which week of each year for all 5 search trends, including global warming, which is not plotted there, that search reached its peak and minimum. Are there any trends you can spot with any of the terms? That is, are some of them drifting later in time or some of them drifting earlier in time? Which term is the largest scatter about its median value? Which term is the smallest scatter? Determine the time lag in units of weeks that maximizes the cross correlation between skiing and spring break. Do this for skiing and global warming. Perhaps you'll find something and you can publish it in Nature. Download whatever trend data you like of your own and sort of repeat this process. So hopefully that's pretty clear. If you go to the next slide, you don't have to do anything. We'll just give you a couple of hints. You probably want to get started with something like this in your various scripts. You can, of course, do this in the notebook and turn that in if you'd like. Numpy has some nice tools for cross-correlation, so you don't have to do that all yourself. If you don't know what cross-correlation is, look it up. Hopefully you'll have some fun with this. Go to the next slide. Just to show you won't have to do anything with this trend data, that Python relative to Java, relative to IDL or MATLAB is taking off. So you're definitely in the right bootcamp. It's good you didn't go to the IDL bootcamp this morning. And I hope as we finish the first day of the bootcamp that you've really seen yourself as a Python programmer in the future. We really only just touched on the surface. We've got 2 more full days of teaching you about Python and software carpentry. So we hope to see you tomorrow morning. If you go back to the schedule, there will be a discussion led by Eric tomorrow morning of the homework, and I think you can also go over any questions about the previous breakout. And we'll start promptly at 8:45 tomorrow with the first lecture, and we'll talk about advanced sort of string I/O.
Or a Python file or something like that. You'll seem very impressive even if your work is not. That's how I've gotten by so far. Array creation and basic operations. I'm going to introduce you to this idea of what a universal function is in broadcasting. They're very powerful tools in Python, but it operates somewhat different from the rest of the things that we've seen so far today. Some basic comparison testing, selection, and manipulation of arrays. The NumPy module provides some basic statistics capabilities. You'll get a lot more in SciPy, which we'll talk about, I believe, tomorrow and Wednesday. And then how to make some basic plots. You want to put nice, pretty things in your paper. The array class. We're going to talk about object-oriented programming. But essentially what NumPy provides is access to this thing called an ND array. Okay? And the ND array is exactly what you think it is. It's an object. Okay? It represents a multi-dimensional. In the same way that a list is, it can have any number of dimensions. Sorry, not in the same way that a list is. It can have any number of dimensions. But what's very important is that all of the items in this array. Okay, so I have a single .ipynb file in this directory. It's called Numpy plus Matplotlib. I just grabbed it off the website. I type Python notebook with a couple extra flags here. Get it up and running. Enter. It automatically takes me, once it gets the kernel up and running, over to my web browser. It starts the notebook and lists all of these .ipnyb files that it finds in the directory that you started IPython in. In this case, there's only one. I go over there. You can see I have a hand now when I select it. I click on it, and it loads that notebook up. Okay? Okay. So here we are. Again, NumPy, which provides you with a capability that we're going to call an array, and Matplotlib plotting. The reason why most of you, we think most of you are scientists. We hope that if you ever get an Excel spreadsheet from someone, maybe think, ooh, I don't know if this person really knows what they're doing. But if you send them a notebook. All right, why don't we get started with the next session? We're running a little bit behind. We don't want to keep you guys here too long. We've been here since pretty early. So we're not going to go over all of the solutions to the breakout session that Paul just gave. We will post those online. If you have any questions, we'll be sticking around afterwards. Feel free to grab us, bother us about some of these things. My name's Brad, by the way. I don't think I met most of you. I'm going to talk about, for the first time, we're going to do some actual, real, substantive, at least the infrastructure you need to do real substantive mathematical calculations. I think a lot of people here are coming from the physical sciences, social sciences, people who are dealing with reasonably large data sets. So the idea behind this session is to give you an introduction to some of the Python packages that you will need to handle large amounts of data. The two packages are called Numpy, and then to actually plot that data called Matplotlib. If you're on the agenda website, there are a couple of different ways you can follow along. I know some people, as it's launching, it shows us here something in our browser. We have a single IPython notebook that's in that directory. It already knows where to look. We fire that up, just click on it, and in a second, it'll have the full notebook here. So you can step through, and almost all, there are a couple changes I made at the last minute, but almost all the code that I'm going to be showing in the slides is in this notebook. So instead of you guys having to type it, you can step through and see what it looks like there. Yes, questions? Sorry, go ahead.
Can you show the code again to put it in
To start up the notebook? It's this line right here. So you call IPython, and then you add the notebook argument to it. That should start up a new window in a web browser if you have a web browser open.
And what additional functionalities are you adding by doing the PyLab and the inline?
I will show you as we get towards the end of the lecture. If I don't, remind me at the end. Yes?
Can we open up the specific .py?
Right, so I'll do this one more time to show you what happens. Let's kill these. I had questions about how to get the notebook started, all that stuff. Right there is a link to the PDF of the lecture slides that I'm going to give, so you can download that and follow along. I also made a notebook with most of the code that's going to be on my slides. You can grab the PDF version, you can grab the raw version and enter it in the notebook itself. I'll show you how to do that in a second. If you just click on the HTML viewer, it renders it in HTML. So you can't actually click on any of these cells. It won't do anything, but you can see what's going on. And if you download the raw notebook and save it within the extension IPMYB, we can fire that up. Just again, start up the notebook, iNotebook, IPython, notebook. I'm going to add 2 flags here because I'll be stepping through some of this. The PyLab loads a bunch of NumPy and Matplotlib packages that are useful, and inline argument tells it to put the plots inline. I'll show you what that means in just a second. But how to load this up, right? We fire up the notebook. It says